AP Calc. I am back with section 2.4, lesson 2. This is pretty much just a tag along for the whole idea of infinite limits and limits that end up being infinite at the end. So, sorry, that didn't make any sense. Limits approaching infinity and limits that involve infinity. So this is sort of like an Owsley made document in which I'm just going to go over some cases that you may have seen some of them already presented to you guys and some of them may be new. Like this one. This is new. So if you guys recall, rational functions that were approaching infinity, the name of the game was dividing by the biggest power on the bottom and on the top. So you divide by the biggest power on the bottom, both top and bottom. For instance, if you saw something like the limit as x approaches infinity of x squared minus 1 over x cubed plus x, something like that. Oh boy, where'd my good marker go? The idea is you could divide the top and bottom by x cubed. The reason why that's helpful is because it creates 1 over x minus 1 over x cubed, a constant divided by a power of x. And on the bottom, it's got a constant plus a constant over the power of x. So limits that approach infinity would zero this one out, zero that one out, and then zero this one out. So it's 0 over 1. You can do the same thing if there's square roots involved. Here's how. The biggest power on the bottom is x to the first. So I'm going to divide that by x. However, on top, I'm going to use an alternate to x. What I mean by that is x can be procured. X can be produced if you took the square root of x squared. Yeah? That's a square root. So if I divide it by the square root of x squared, I'm technically dividing both the top and the bottom by x. So a root divided by a root is just the root of one fraction. So you can bring the x squared into all parts of this. You got 2 over x squared, negative 3x over x squared, and plus 11x squared over x squared. Underneath the root, of course, and then on the bottom, these x's would cancel, so you've got 7 minus 9 over x. Now, the limit as x approaches infinity of the square root of a constant over a power of x, a constant over a power of x plus a constant would be 0 minus 0 plus 11 over 7 minus 0. 7 minus 0. That's what happens when I apply the limit to these parts, which leaves you with root 11 over 7. Let's check out what happens when you approach negative infinity, because it is different. It doesn't seem any different, but I kind of glossed over something when I said the root x squared equals x, I was fibbing just a little bit. There is a rule when you take an even root and you get an odd power on the outside that you must put absolute value bars around it. Here's why. Take the square root of 2 squared. That equals the square root of 4, which equals 2. Great. What does that have to do with this? Take the square root of negative 2 squared. Negative 2 times negative 2 is also 4, which is 2. So it's sort of like this idea of working backwards. You don't know if you've got a positive 2 or a negative 2 when you unleash. Take away the root. Because here's what we're really doing. When we say the square root of x squared is just x, we're saying take away the root and the square, and that's what we got. But if you did that with this one, you're coming up with all sorts of trouble. So you got to put absolute value bars. And then you have to think in terms of the absolute value of x is the same as negative x. Remember when we turned absolute values into piecewise functions? Negative x when you are less than 0. And your x when you're greater than 0. And in this case, one of them is equal to. And the implication to this is that this one represents the limit as x approaches negative infinity. This one represents the limit as x approaches positive infinity. So, when we divide the top by root x squared, we are dividing by this on the bottom, which is actually this, which splits up into 2 different parts when you talk about limits approaching negative infinity and limits approaching positive infinity. So I have to use this version to divide the bottom out. So the same things will happen inside of here. This will be negative 7 plus 9 over x. This x will cancel with 1 here on the bottom. Both of these will cancel. Applying the limit as x approaches negative infinity will still zero out this term, and this term. So you got root 11 over negative 7 now, which creates a negative fraction here. All right. Kind of heavy, but hopefully you guys followed the logic of all that. Now, one thing that I wanted to talk about also is what happens if it's not just an x down below and an x squared above, but what if there's bigger powers? Well, the only thing that I really wanted to talk about was the relationship between the square root of x to the fourth and x squared. The question is, do I have to put this in absolute value bars, just like I did before? And the answer is no. Here's why. X squared is this parabola. It's a number times itself. A positive times a positive is above the x-axis, positive. A negative times a negative is positive above the x-axis. There's absolutely no need to distinguish between positive infinity and negative infinity because every x value approaches positive infinity when you plug it in. The limit as x approaches positive infinity versus negative infinity is essentially going to be the same thing. So no absolute value bars. You can divide the top, well, you divide the bottom by the x squared and the top by root x to the fourth. So root x to the fourth. So what happens here? They cancel. They cancel. They cancel. So apply the limit as x approaches infinity, and you're left with 2 minus 0 over 0 minus 7. Root 2 over negative 7. So then your work would be identical. Over here. Same exact thing. Yeah, so by the way, guys, did you notice that the leading coefficient ratio, as long as the outside of the root is exactly half of the inside of the root, it's just going to be the ratio of what you see there, if you don't have absolute value bars. So there's a shortcut there. So this last one attempted to sort of like put into place what the actual, hold on. So what I wanted to do with this last example is just show how the trend moves. Even root to odd power, x to the 1, yields absolute value bars. Okay? Square root x to the 4th yields an even power here. No absolute value bars. Root x to the 6th equals x cubed. Odd power yields absolute value bars. Which means the limit as x approaches negative infinity, you would use negative x cubed. The limit as x approaches positive infinity, use positive x cubed. And at this point, we can use that shortcut of the ratio of the leading, I'll call it powers, as long as you have a 2-to-1 ratio between the root inside. Like this matchup has to happen, all right? So that if it was the square root of x to the 500th power, You got to have exactly half of 500, x to the 250. Which, by the way, it's even, so you wouldn't put absolute value bars around it. So we would be most concerned with the 2x cubed, the 2x to the 6th power, and the negative 7x cubed. If the limit as x approaches positive infinity, then you are using basically a positive x cubed to divide that out. So it leaves negative 7x cubed unchanged as far as its sign. It's still negative. So this right here, come on now, different color. Root 2 over negative 7 is what you would use for number 4. Which is, you really should write it like this. So what does that look like on the other part? Because it's negative infinity, this right here is going to change negative 7 to positive 7 in the final limit. Because you'd be dividing by negative x to the 3rd power, creating a positive 7. So it's root 2 over negative 7. All right. Hopefully that was engaging and is helpful for the assignment. Part 2 coming up.